this video, we're going to be talking about Green's identities. Now, these provide the mathematical justification for panel methods. You know, why they work, why we can do what we do. You can get at panel methods just from kind of the superposition of elementary potential flows idea, but this is a little more fundamental, a little more rigorous. There is a lot of math that goes into this, and I'm not going to dive into all of it. If you are interested, most of what I'm going to be presenting comes out of Kellogg's Foundations of Potential Theory, Chapter 8. So if you're really interested in more of the deep math, dive into that book, but we're just going to give an overview here, and I'm not going to try and be super rigorous about it. I just want to give everyone an idea of what's going on. So, Green's identities, there are 3 of them. We're going to start out with our first one. To do that, we're going to pick just 2 functions. These are arbitrary functions, u and v. And what we say is that u and v are defined on some region R, which has boundary S and outward normal N. Okay? And I think to be consistent with things, I should do that as just a regular line. Okay, so u and v are defined in this region R, and we say that the only stipulation we're going to make on u and v is that they're continuous and continuously differentiable to the second order. So we can take first derivatives, we can take second derivatives, and those results would be continuous. Okay, so if we do that, we can take and we can define a vector field inside R. We'll call it F, and we're going to define that vector field as v times the spatial derivatives of u, so partial x, v times partial u, partial y, and v times partial u, partial z. Okay, and if you notice, if you look at this, we can pull v out of this whole thing, and then what this vector is just the gradient of u. So we've got v times grad u. Okay, that's our vector field that we've defined. Now, what we're going to do is we're going to apply the divergence theorem to this vector field. Now, if you remember from your multivariable calculus course, the divergence theorem is as follows. We say that the volume integral of v over v, or I guess I should say r here, my bad. Volume integral over R of grad dot f, and gradient dotted with a vector, that's the divergence of the vector field, times dr is equal to the integral over the boundary of R, so S, of f dotted with n, that outward normal vector, ds. Okay, so let's take and plug our vector field into the divergence theorem here. Okay, if we do that, we're going to have, help if I turn draw with touch back on. We're going to have the triple integral over R of grad dot, and remember our definition for f, v grad u dr is equal to integral over s of n dot with v grad u ds. Okay? Now for this first term here on the left, we need to apply the product rule. So we're taking this gradient vector is a derivative operator, so if we want to apply it to v times grad u, then we need to use the product rule. So let's distribute that through. Come on. There we go. My stylus is a little finicky these days. Okay, so the triple integral over R, let's apply it to the first term. We get grad v dotted with grad u, and then applying it to the second term, plus v grad squared u dr. Okay? If you're a little shaky on that, pull out your calculus textbook and review the product rule, review some of your the gradient operator. And then let's do the right hand side now. V is just a scalar that's multiplying this vector, grad u, and so the dot product goes only onto the vector part of it. So we've got integral over s of v times, now if you'll remember, again from multivariable calculus, if we take a unit vector dotted with a gradient, what do we have? Well, we have the derivative of the function in the direction of that vector. So we can write this as partial u partial n ds. Okay? And there we have it. This is Green's first identity. Okay? Now remember, all we've done, we defined a couple arbitrary functions, we said something about their continuity, we said they're defined in this region R, and we can apply the divergence theorem and get to this result here. Okay? Now, let's move on. We're going to go to Green's second identity. Now, remember we were kind of arbitrary here when we defined f. We said that it's, v times the gradient of u. Well, we could define it another way. We could say that f is u times the gradient of v, and we would go through this all again and we'd get Green's first identity, but just with vu and v switched places. So let's go ahead and write out what that would be, and just to be painfully clear here. We would end up with the triple integral over r of, remember we're just switching places, grad u dotted with grad v plus, and now I'm being a little pedantic writing this this dot product here in reverse order. If you'll remember, the dot product is commutative, so it really doesn't matter which order we write that in. But I'll just switch it just so we can be clear that's what we're doing. Plus u grad squared v dr is equal to double integral over s u partial v partial n ds. Okay? Sweet. Well, again, this is just another form of Green's first identity. We've just swapped the places of u and v. Now, if you'll notice, we've got one term that's in common between these two. This term, again, like I said earlier, they're identical. So let's take these two functions and let's subtract them from each other. So, doing that, we're going to end up with, and we want this to cancel out this this dot product term here that we have. So, eesh. It's a horrible integral, but you get what I'm doing. Triple integral over r. Let's do this bottom function minus the top function, or sorry, equation, not function. U grad squared v minus v grad squared u dr is equal to, now again, these two terms just cancel each other out, so we don't need to worry about them. Moving on to the surface integral, doing bottom minus the top, u partial v partial n minus v partial u partial n ds. Okay, and believe it or not, we have already reached Green's second identity. That is this equation right here. So all we've done, we've started with the first identity, we've swapped u and v places, we subtracted them from one another, we've ended up at Green's second identity. Now I'm sure you're wondering right now, where on earth is this all going? This seems kind of useless right now. Don't worry, you stuck it out to this point, now is where it's going to get good. We're going to get to the derivation of Green's third identity, and this is where we find something some really useful results for panel methods and what we're going to be doing in this project. Okay, so up until this point, again, we've said that u and v are just arbitrary. They're any functions we like. As long as they satisfy those continuity conditions, they can be whatever. Let's go ahead and define one of them. And we're going to define v is equal to 1 over r. Okay? And we're going to define a point. We'll call this point P. And P will have coordinates x, y, z. Okay? And we'll consider P to kind of be the origin of V. So r here is the distance from any point from P to any point that we're considering. So we'll call that point Q. And it's got coordinates c, eta, zeta. Okay? So to be explicitly clear, r is equal then to the square root of x minus c squared minus y minus eta, plus y minus eta squared plus z minus zeta squared. Okay, so we've defined v, and now we've defined v in this way because v satisfies Laplace's equation everywhere except for at point P. So if we've got, for any region not including point P, v satisfies Laplace's equation. Grad squared v is equal to 0, which is a really useful result for us. As a note, if a function satisfies Laplace's equation, we call that harmonic. So if you hear me mention harmonic functions, a harmonic function is just any function that satisfies Laplace's equation. Okay? Don't get too mixed up in the definitions. So now let's try and plug this back into Green's second identity. The only problem is that, like we can't consider the point where P equals Q, because if we've got that, then R equals 0 and V blows up. So we need to exclude the point P from this region that we're looking at, the region over which we have defined Green's second identity. So what is that? What are we going to do? Well, we've got our region R, right? We've got its boundary S. And we've got its normal vector pointing out of the region. And let's say point P is right here. Okay? We're going to exclude point P from R by drawing a little sphere around it. And that sphere we're going to call sigma. Now I'm not going to draw it here, but N on sigma is going to point inwards towards P. And that's again because we're pointing out of the region R. And we're going to say that we're going to define a new region, R prime, which is equal to R is R minus sigma. So everything in R excluding what's inside sigma. Okay. Now let's go ahead and rewrite Green's second identity over R prime. Now you'll notice that this first term here, the very first term, is going to vanish. And why is that? Well, because we said in R prime, V is harmonic, and so this grad squared V term is identically 0. So because we're considering R prime, that term goes away. We don't have to consider it anymore. Okay? How convenient for us. So we're gonna start out with just that second term, and that will be triple integral over R prime of, again we've defined V is 1 over R, times grad squared U dr, okay, is equal to, now we're doing our surface integrals. The surface integral is going to remain unchanged for now, U, except now we've got to deal with 1 over R instead of v minus 1 over r times partial u partial n ds. Well, now what we need to remember is that we've augmented the boundary of r. Since we're now dealing with r prime, the boundary of r prime is s and sigma. So we need to write this for sigma as well. So plus the double integral over sigma of u partial n times 1 over r minus 1 over r partial u partial n ds. Now you might be saying here, wait a second, shouldn't we be subtracting that since we've removed this sphere from r? Well, no, because we've defined that n is pointing outward from r prime, it's going to point into sigma, and it's going to take care of that sign difference for us there, okay? Well, this is all fine and dandy, but it seems like we've gotten more complicated than what we started out with, which is a little frustrating. So, let's see if we can simplify things. Obviously, it's really not convenient to be carrying around this little ball that surrounds P. We'd like to get rid of that. So let's see what we can do to this last term here if we say we're going to take the limit as sigma goes to 0. Okay, can we do that? Let's go ahead. In order to do that, we're going to rewrite this last term. Instead of in terms of a surface integral, we're going to rewrite it in terms of an angular integral, in particular in terms of solid angle. Now, solid angles are a little odd, but if you think about it in 2 dimensions, think about if you're integrating over the surface of just a circle, you can pretty easily transform between, you could do that as a line integral, or you could do that as an integral in theta, in the angle of the circle. You can do the exact same thing in 3 dimensions. You can do a surface integral in terms of the surface, or in terms of what's called the solid angle. And here we're going to denote the solid angle by, or the surface in solid angle by omega. So we're going to rewrite this. We're going to rewrite this term as the double integral over omega. And again, omega is just sigma expressed in terms of solid angle of u times partial n 1 over r minus 1 over r partial u partial n. Now to transform, again, think of this in the 2-dimensional case. If we're going from a line integral to an angular integral, we need to multiply by r in order to get the proper change of coordinates. We do the same thing for solid angle, but instead we multiply it by r squared. Because our solid angle is dimensionless quantity, we're doing a surface integral, we need to multiply by r squared to get to the proper result, d omega. There's a couple things we can do to simplify this to get to a better form before we actually evaluate some of this integral. One thing we can do is we can recognize that on this sphere, if this n vector that's pointing inward is always going to be opposite our radial direction. So n is always the negative of e hat r. And so any derivative that we want to take with respect to n, we can change that into a derivative with respect to r just by taking the negative of it. Okay? So we can take this term here and we can rewrite it as the double integral over omega of u partial gee, I forgot a sign there. Negative u partial r of 1 over r, and then we can do the same thing here, plus 1 over r partial u partial r times r squared d omega. Okay. Well, we can evaluate this partial r of 1 over r. That's just going to be negative 1 over r squared. The negatives will cancel each other out. And we'll end up with, and we can bring, or actually not quite yet. Let me scooch this down. This will become the double integral over omega of u times 1 over r squared plus 1 over r partial u partial r times r squared d omega. Okay, let's bring the r squared inside the parentheses, and that will give us double integral over omega of u, the whole r term just goes away, ain't that convenient, of r times partial u partial r d omega. Okay? Well, now we're to the point where we can actually take the limit and say, okay, what's going to happen as r goes to 0? Well, this first term, we can, even before we take the limit, we can say that this is just going to be some, we can use the mean value theorem to say that this first term is going to be some mean value of u on sigma, or inside of sigma, multiplied by double integral over omega of d omega. Okay? And then the second term stays the same. R partial u partial r d omega. Well, the integral over omega of d omega is just going to be omega, and our limits of integration for solid angle integration over an entire sphere is just 4 pi. And so this first term here becomes 4 pi times u, some average value of u. Now if we take the limit as r goes to 0, well, the average value of u inside this infinitesimally small ball is just u at point P. So we can get rid of the average thing, and we can just say this is u of P. And then as r goes to 0, this r right here will go to 0, and so this whole term just vanishes. Okay? So that was a really long derivation that we took to be able to say that this term right here, highlighted in yellow, is simply equal to 4 pi u of P. Okay, so we've managed to get rid of that little ball sigma. We don't have to keep carrying that around. We can write things now really simply in terms of just this value of u at P, multiplied by a factor of 4 pi. Okay, so let's substitute that back into our equation that we had up there. We're going to end up with negative triple integral over r. So now we've taken sigma, we've shrunk it down to nothing, and because we've done that, r prime has become r. Okay, so we can go back to the triple integral over r of 1 over r grad squared u dr is equal to double integral over s of u times partial n, oh, not partial n, partial n, partial n of 1 over r minus 1 over r partial u partial n multiplied by ds, and then that second term has just become plus 4 pi u at point P. Okay? Ain't that nifty? We've really simplified things down now. And we can go ahead and rewrite this in a specific form. We're going to write it as, I'll swap colors here, we're going to get u of p all by itself. So u of p is equal to negative 1 over 4 pi, the triple integral over r of grad squared u over r dr plus 1 over 4 pi times our surface integral term. S partial u partial n 1 over r minus u partial n 1 over r ds. Okay? And that, ladies and gentlemen, is Green's third identity. And this is where we'll leave off for this video. I just want to make a note of what is this equation saying. This equation is saying that if we have some function u, which is defined inside R, and it is continuous and continuously differentiable, then we may express its value at any point p inside R as contributions from a volume integral of the Laplacian of u plus a surface integral involving the normal derivative of u on the boundary and the value of u on the boundary. Now this is really powerful, especially when we can say that the Laplacian of u is 0. I'll get into that in the next video, and we'll talk about how panel methods arise out of this.